Hi, welcome to our 15th lecture on combinatorics. Last time we introduced the Gaussian coefficient and we discussed some of their properties. Today we'll continue studying these coefficients and describe other properties that they satisfy. So as you recall, we defined these parameters that depend on q as 0q is 1, and for n greater or equal to 1, nq equals n when q equals 1, and it equals this ratio of q to the n minus 1 divided by q minus 1 if q is not 1. You can think of that as the number of non-zero vectors in a vector space of dimension n over the field fq. And using this notion, we defined the q factorial, and this is defined recursively. So when n equals 0, it equals 1. And then if you want to calculate nq factorial, you just multiply nq times the previous factorial, the n minus 1 one. And if you unpack this recursive formula, you realize that when q equals 1, this q factorial coincides with the usual n factorial. And when q is not 1, we have this product of n factors of the form q to the k minus 1 divided by q minus 1 when k goes from n all the way down to 1. Now, after that, we define this q binomial coefficient, and this is what we mean by the Gaussian coefficient, is this parameter n choose k. And this is defined as the number of k subspaces of an n-dimensional vector space over fq. And here, if it makes it easier, you can think about this this vector space as being fq to the n, the Cartesian product of fq to the n with the usual addition. Now we proved that this q binomial coefficient or Gaussian coefficient has a similar formula to the one for the usual binomial coefficient, in the sense that it equals the ratio between a factorial, this nq factorial, and the products of kq factorial and n minus k factorial. And this expression can be further simplified to have this q binomial coefficient expressed as a ratio of something similar to the following factorial from our previous results. So you see on the numerator, at the equation at the bottom of the page, we have a product of k factors, and the exponent starts at n and it goes down all the way to n minus k plus 1. Whereas at the bottom, we have also a product of k factors, the exponent of q starting at k and going down all the way to q. And in the previous class, we also showed that this q binomial coefficient is actually a polynomial in q, and we express of degree k times n minus k, and we express the coefficients of q of this in this polynomial in terms of numbers of partitions of a natural number whose Ferrer's diagram fits the box of size k and n minus k. Okay, so that was a quick recap of our previous result. Now we are going to describe some more results involving this Gaussian coefficient, and I will try to keep the same parallel as in the previous results between the results that we have for sets and the results that we have for subspaces. So for subsets and for subspaces. Okay, so let's start with the result that we know for sets, which is that n choose k equals n minus 1 choose k plus n minus 1 choose k minus 1. And proof for this result, I think we gave a proof in our previous lecture. There's a easy proof by just algebra, but it's not very insightful. You just plug in the formulas in the into the right-hand side, then it works out to be the left-hand side. The better proof is to see that both sides count the same quantity. So the left-hand side counts the number of k subsets of the set n, and the right-hand side, n minus 1 choose k counts the k subsets of the set n minus 1, and n minus 1 choose k minus 1 counts the k subsets of the set n that contain the element n. And it's clear that if you look at the k subsets that are counted by the left-hand side, you can partition them into those k subsets that contain n, and those k subsets that do not contain n, which are the same as the k subsets of n minus 1. And therefore, the left-hand side will equal the left-hand side of our identity on the top will equal the sum of these two binomial coefficients. So that's how I read this binomial formula when I see it. Now, what happens for subspaces? Well, surprisingly, there are two actually. They're equivalent, but there are two formulas that generalize this one. So we'll just start with one. So for subspaces, we're going to have something like this. If we take this q-binomial coefficient, will equal n minus 1 choose k plus, here is a surprise, there's a q to the power n minus k times the expected binomial coefficient n minus 1 k minus 1 choose q. Okay. All right. So how do we prove this result? Well, again, you can prove this result if somebody told you to, gave you the formula and ask you to prove it. Again, you can do same as before, a non-insightful proof of it by just plugging in the values for the right-hand side and doing some algebra and simplifying things and ending up with a result on the left-hand side. But let's give a second proof, okay, showing a little bit kind of the deeper meaning of this result. So let's just think of so we have our vector space, the big one. Let's call it FQN. And we want to count the number of k subspaces here. That's what the left-hand side is. Now, inside here, let's take H. So this represents H. Let H be a hyperplane. So be a subspace of FQN of dimension n minus 1. And this H, in some sense, plays the same role as the set n minus 1 from before, from the left-hand side. So in the case of the sets, we counted the k subsets by splitting them according if they're contained in this smaller set n minus 1 or if they're not. Okay, so that's the same thing that we'll do here. So if we take, if we look at the k, a subspace of dimension k, okay, we are going to consider two cases. The first case is if k is actually a subspace of H, and the second one is obviously the complement of that when k is not a subspace of H. Okay. Now, if k is a subspace of H, so if k lives here, which is in this case on the left side, then H has dimension n minus 1, and k is capital K is a k subspace of it, and so there are exactly n minus 1 choose k such subspaces. Okay, so that's pretty easy. Now let me use a different color of what happens on the other side. So if k is not contained in H, so let's say if k is something like this, okay, then there is a part of k that's inside H, and that part is k intersect H. when you intersect two subspaces, you get another subspace. So this K intersect H is going to be a subspace of H. Okay, that's the one here. And I leave it to you to work out that the dimension of K intersect H equals K minus 1. Okay. So now we are trying to count such subspaces, H. So to do that, we are going to count them according to this intersection of them with the hyperplane, or with this n-1 dimensional subspace H. So let's just give this K, let's call this K intersect H, let's call it L. And because L has dimension K minus 1, and this is L here, and L is contained in H, we know that there are n-1 choose K minus 1 such L's. Okay. Now, let's pause for a second and look what happened, for example, in the previous situation with the sets. So let me draw it here on the left-hand side. Here I had the set n, and inside it I had, well, let's draw a similar picture to the one. Here, this is maybe the set n-1, and here you have the element n outside it. And the n-1 choose K part counted all the K subsets that live like this. And the n-1 choose K minus 1 counted all the ones that are of this form. And here, this part, this is the part that it's the equivalent of our L, and the big set is K. So in the situation of the sets, the number of L's, if you look at these L's, we had n-1 choose K minus 1 of such L's. And for each such L, there was only one way that you can extend it to a K set. Basically, you just add the element n to it, and it gives you to n-1 choose K minus 1 such Ks. Okay. In the situation of the subspaces, things are a little bit different. You don't just have one way of extending a given K minus 1 subspace from this hyperplane to a K subspace in the big plane that is not contained in H. So we want to, again, we have this number of ways, n-1 here at the bottom on the right, n-1 choose K minus 1. And we want to count the number of K subspaces now that contain this part and do not live inside, are not subspaces of H. Okay. So how do we count that? Well, if we're given a certain K minus 1 subspace like L, so if we fix L, I'll just squeeze in here. Maybe I'll just erase here because we know what H is. Okay, so we fix the L, and then we have two things: the number of K subspaces. Let me just use shorthand. Number of K subspaces containing L is going to be n. L has dimension K minus 1, so it's going to be n minus K plus 1, choose 1 here. And this is, you can do it with the way we did it in the previous lecture, where we counted the number of chains. If I give you a subspace of cardinality of dimension J, how many subspaces of cardinality J plus 1 contain it, and so on. So you can use that formula. Okay, and now So this is a number of K subspaces that contain L, but I don't want to count all of them. I want to count only those that are not inside H. So to do that, I count the number of K subspaces that contain L, the number of K subspace inside H that contain L. And now H is an n-1 dimensional subspace, and you have this k-1 dimensional thing in it, so that is n-k, choose one. Okay, so from these two things, the number of subspaces that I want, the number of k subspaces containing L and not in H, that number will equal the difference between these two values. So it will be the, maybe I'll write it here at the bottom, will be n minus k plus 1, choose 1, minus n minus k, choose 1. And that will give us, it's actually q to the n minus k if you do the calculation. All right. So then that explains the second part of our formula, because we agree that we have n-1 choose k-1 such L's here, k-1 dimensional subspaces. And for each such subspace, they're exactly q times n minus k subspaces k that contain them and do not lie inside H. And so that finishes our proof that the binomial coefficient, the q-binomial coefficient n choose k equals n-1 choose k plus, there's a twist here, q times n minus k times n-1 choose k-1. Okay. So there are similarities in the methods, but things are not quite the same when you go from subsets to subspaces. So let's keep this parallel here. So we have subsets, we have subspaces. Okay. Now, I mentioned that there are two formulas analogous to this one on the left. To get to that, let me give you a simple result, which is the following. That so for k subsets, we know that n choose k equals n choose n minus k. And again, here, proofs. One is again algebra, just plug the numbers. But second, it's again more, that's the way you can remember this easily. It's a bijection from the k subsets sets to the n minus k subsets, sending A to the complement of A. Okay. Now you can imagine where we're going with this. For in the case of subspaces, there's something similar. So you can have n choose k is the same as n choose n minus k, and proof. The first one, again, it's just the formulas, so algebra. So you can figure out it's obvious, it's pretty simple. And the second one, try to do a bijection. So I'll leave it to you as an exercise to think how you can do a bijection from the k subspaces to the n minus k subspaces. So yeah, think about it, and I'll be happy to talk to you if you have questions. Okay, so with that in mind, so before we had this n choose k equals n-1 choose k plus n-1 choose k minus 1. And here we have the q-binomial one. So what you can do here is this formula is equivalent if you you use the equation on the top, if you go to the complement in some sense, and you go n, choose n minus k equals n minus 1 choose n minus 1 minus k plus q to the n minus k times n minus 1 n minus k. And now I'm going to do just a change of variable. So what I will do is let me denote L to be n minus k. And what does that give me? Well, I will get n choose L q equals, what do I have here? I have n minus 1 on the top, but on the bottom I have L minus 1. And this one is QL n minus 1 choose L. And I mean here, I hope I don't trick you with so many substitution. If you want now, you can replace L by any letter that you like, including K. And you will end up with the following formula, which is n k equals, in this situation, let me write it as q to the k times n minus 1 choose k plus n minus 1 choose k minus 1. And you see that this formula that we get here at the bottom, there should be q's here. Again, if you take limit as q goes to infinity, this formula gives you this, and also this formula gives you this. If you take q goes to 1, q goes to 1, okay? But this formula, these two formulas, they're a bit different. I mean, I just showed you that they're equivalent, but the one on the top that we just proved on the previous page and the one on the bottom, the coefficients are different. So what I want to give you as an exercise to give a self-contained proof of this result, not using the previous result. So try to do a counting, a bijective proof, similar to the one that we gave on the previous page, in which you start with the k subspaces, which are counted by this n choose k, and then you split them according to some rule, and then see what you can get to end up with the formula that we have there. Okay. All right. Now, okay, let's keep this subsets and subspaces. Okay. So let's go to other formulas that we have for subsets, and one of the most important ones is the binomial formula, where you have if n is a natural number and a, b are real complex numbers, a plus b to the power n equals summation from k equals 0 to n of n choose k, a to the k, b to the n minus k. And now for these formulas, we gave a proof, direct, first proof we give is direct, just count, figure out the coefficient of a to the k times b to the n minus k. You can give a second proof using induction on n. You have a formula for a plus b to the n. To get a plus b to the n plus 1, you just multiply a plus b to the n times a plus b. Okay. So now what happens here with the q-binomial formula? So there's several things here. So first of all, you can have a situation where you have what are called q-commuting variables. And this can be sometimes like linear operators. So we can have two commuting linear, q-commuting variables, a and b, which means that b times a, you have some product, and b times a equals q times ab. So of course, if q equals 1, this is the usual product that we think of. But There are some examples. I won't go into them now, but there are some examples of such objects where the product satisfies this relation. And then you can, when you calculate a plus b to the power n, it's not as simple as, so you see every time you change the order from b to a, you gain a factor of q. And the amazing thing is that if you do a plus b to the n, you end up with summation from k equals 0 to n of n choose k, the q binomial coefficient, a to the k, b to the n minus k. Okay. And now for a proof of this result, a direct proof is a little bit tricky because it's hard to interpret these coefficients and so on. So you can mimic the second proof. So you can do a proof by using induction on n and the previous identities that we proved for the coefficients of the q binomial coefficients. Now again, from this formula, there is a way, but I won't do it here because it will take a bit of time to get to the next formula, which is a kind of not a q binomial. And this is most of the time, this is what it's coded as the q binomial formula, which is the following: that if you take the product, let me use red. If we have q and now we have another variable t. If we take the product from j equals 0 to n minus 1 of 1 plus q to the j times t, this equals the summation from k equals 0 to n of n choose k, the q binomial coefficient, q to the power k choose 2, and t to the power k. Okay. So I will use that formula in a second. And for this formula, so this proof, again, you can do a proof by induction on n. So you have this this product of the factors are not all the same, but you have these powers of q that that increase, and you will get as in the terms of the summation, q to the power k choose 2, t to the power k, and the coefficient will be this q binomial coefficient n choose k. Now, if this formula here implies this one here, you just take q equals 1. Or you can, if you want to be more careful, you can take q goes to 1, because if you take q equals 1 into the q binomial coefficient, you get impossibility, you get 0 divided by 0. So it's better you take a limit as q goes to 1. Okay. Well, that's another formula that's the same. Okay, let's do one more. Okay, maybe I shouldn't have erased here, sorry. Okay, so let's do one more. I think there's another formula we discussed, this convolution or van der Waal identity, which says the following: if I look at the binomial coefficient m plus n choose k, you can write this as a summation from j equals 0 to k of m choose j times n choose k minus j. And the proof, again, the easy way to remember this is you have the objects from 1 to m. So when you look at the set with m plus 1 elements, you can think of it as formed by n elements here, and you have m elements here. And now when you choose k of them, you're choosing k of these elements, k subset. k subset, and the number of such k subsets is clearly m plus n choose k. When you're counting these k subsets, you can count them according to what the intersection is with the first part, which is size j. And if that intersection is size j, then since this is a k subset, that intersection has to have size k minus j. And so the number of k subsets is the same as the number of j subsets of the set 1 to m times the number of k minus j subsets of the remaining set from m plus 1 to here it's not n, it's m plus n. And that can be done in all possible ways. J can be as low as 0 and can be as high as k. So that's essentially the proof by a picture. Now, what happens in the Q situation for this Gaussian coefficient? Well, you have a similar formula, but again, there will be a twist. So you have m plus n of choose k. So you're counting the number of k subsets, k subspaces of a space of dimension m plus n. This will be summation from j equals 0 to k as before. And you have here m choose j with a q and n choose k minus j as before. But you don't have just one way of putting these things together. You are going to have q to the power m minus j times k minus j. Okay. Again, when q goes to 1, the formula on the right implies the formula on the left. And now, okay, I didn't give you a proof of this result. The proof, you can do a proof similar to the one that I did here by counting subspaces, but perhaps the easiest proof here is actually algebraic. And the algebraic proof mimics an algebraic proof for the set situation. So let me tell you the algebraic proof for the set situation. So let me erase here. Induction. So for this result here, you can do a proof by looking at 1 plus t to the power m plus n. You write it as 1 plus t to the power m times 1 plus t to the power n. And consider the coefficient of t to the k in both sides. So coefficient of t to the k in the left side, it will be m plus n choose k. And coefficient of t to the k on the right-hand side, it will come from a t to the j from here and a t to the k minus j from here. And when you spell that out, it gives you summation from j equals 0 to k of m choose j and choose k minus j. Okay, so that's the proof by algebra, and it's equivalent to this counting proof. Now here, let me give you the sketch. I won't go the whole details of the proof for the q-binomial identity, and that follows from using the binomial formula here on the top. And how do you use it? Well, you write first the product from j equals 0 to m plus n minus 1 of 1 plus, well, what do you mean don't use I here. Or, yeah, let me use I equals 0 of 1 plus qi times t. And this equals, by the binomial formula, summation from k equals 0 to m plus n choose k, q to the power k choose 2, and t to the power k. Okay. Now, the same formula from here before, in the case of sets, it broken down very easily in this kind of symmetric form. in terms of M1. And here it's a little bit symmetric. And so you break it down into the product from I equals 0 to m minus 1. So this is kind of equivalent to this part of the set, 1 plus qit times the product, the remaining part, which is from j equals 0 to n minus 1. And in that situation, you have all the powers are q to the m plus 1, and so on. And you write them, you pull, it's q to the j times q to the m times t this way. So here, you use the binomial formula on the light blue side to get an expansion, and you use here the binomial formula on the dark blue side, using as the t this q to the m times t. And then you base the whole thing is about identifying the coefficients of t to the k from both sides, from the top formula and from this product. And you end up with this, by identifying the coefficients and doing some algebra, you end up with the result. Okay. So again, the situation of the q-binomial formula and so on, there are similarities with the situation for subsets, but there are also some things that are quite different. Okay, I'll give you one more example and one exercise, and then I'll finish up. Okay. So let me give you a simple proposition for the realm of subsets. So let's say we have n a natural number and A is a subset of n. You fix a subset, and let's say A has cardinality k for some k between 0 and n. We're asking what's the number of subsets B such that B has n minus k elements and B is skewed to A, so B is disjoint from A. And this is an obvious question for sets. The answer is 1, because B has to be the complement of A. There are no other choices. Okay. Now, let's ask a similar question in the realm of vector spaces. So let's consider K be a vector subspace of our space FQN with dimension of K, capital K, equals K. Okay. The question is, what is a number? And this can confuse people in many situations. The number of subspaces L such that dimension of L is n minus k, and L intersect k. In the case of subspaces, you cannot have empty intersection because everybody contains 0. So, but yeah, that's the equivalent of, in some sense, having empty intersection. The dimension of their intersection is 0. So we're asking, what is the number of subspaces L such that the dimension of L is n minus k, and L and Q are, so that sometimes this is called L and K are skew. Or you can think of complements of each other, but yeah. So what's the formula? Well, it's not one, actually. And the number of such subspaces is q to the power k times n minus k. Okay, so this may seem a bit strange, but let's try to work out through a proof. Okay, minus k. Okay. So here's how we can think about the proof. We can think of k as taking a basis and putting it into a matrix, and you can think of k as a k by n matrix. Let's call it M. That has rank. It has rank k. And now we can do all this row reduced echelon form, and we can identify k. And without loss of generality, let's assume that the leading ones in this matrix are in the smallest possible position, 1, 2, 3 up to k. So let's just assume, if not, the proof is similar, but it's a bit more messy to draw, as you'll see in a second. So let's assume that this matrix M is of this form. You have identity on the first side, and you have something on the second, some M prime on the second side. So you have here the dimension of this is k, and here you have n minus k, and here k. Okay. So I'll use the space here. So don't I don't want to move to another page. Sorry. Okay. So now, what are we counting? We're counting the L's, and now the K has this shape. Okay, let's say IK and M prime. N has its own, L has its own matrix. You can take a basis for it, and you can put it here. Let's say it's, so what do we have here? Maybe something like this. It has n minus k, this is k, and both of them have n columns. And so you take a basis for L, and you put these vectors as row vectors in this matrix. And let's say you have an n1 here and you have an n2 here. Now, because k and L are skew, it means that when you put these rows together of these two matrices that you see on the left-hand side, this matrix has to have full rank. So this matrix that you obtain by combining this, so it's a matrix that you obtain by gluing, putting these matrices on top of each other. IK here, M prime, N1 here, N2 here. This matrix has to be invertible. And this comes because K and L are skew. So together they, they give you they put their bases together, they give you the basis for the whole space. Okay. And now this matrix is invertible. That's actually equivalent. If you do a bit of linear algebra, is equivalent to N2 being invertible. This small matrix here, which is n minus k by n minus k. But what happens there, if you look at this matrix, if you look at the row space of this matrix here, n1 and n2, as we learn from linear algebra, if you multiply this matrix to the left by an invertible matrix, the row space stays the same. The row space there, it's the same as the row space of this matrix. If you multiply to the left by n2 inverse, you're going to get n2 inverse n1 times I n minus k. So when we are looking at this matrix that is invertible, so L, the row space of L can be thought of as N1, N2, but the row space of L, you can think of it by this argument as the row space of N2 minus 1, N1, and here I, N minus K. Okay, and so how many such L's, if I want to count the number of L's, it's the same as counting the number of these bases, it's of these matrices here. Yeah, that I'm hiding something under there, but that's the case. And how many such matrices we have? Well, the identity in that bottom corner is identity. There's not much there. But if we look at this matrix here, it has k rows. It has n minus k rows, and it has k columns. Therefore, the matrix has k times n minus k entries, and that each of that entry can be filled with an element from the field which has q elements. So number of L's is going to equal the number of matrices in that bottom left corner, which is q to the power k times n minus k. Now again, if we get take q in the limit to goes to 1, you get a trivial result from the left corner. But this result for the subspaces, as you see, is far from trivial, and it's quite more involved than the one for sets. So now I'll just finish with one exercise to give to you. Maybe I'll put this on a homework. 6. So let's say this is just in the subspace. Well, I can write it in both situations. Okay. So let's say, let's draw it by a picture. Let's say we have our set with n elements, and we have here a k, so size of k is k, and we want to count the, so let k be a subset of n, cardinality of k is k, the number of subsets L such that cardinality of L is L, and cardinality of the intersection between L and K is some fixed number J. So we have the J there, this is L, and this is the intersection L intersect J. Well, what is a number? So we are given a fixed subset, K subset, and we want to count the number of L subsets that intersected in cardinality J. So if we pick this intersection J, we have K choose J such choices. And for each such choice, we can pick the remaining L minus J elements of L from a set of cardinality n minus K. So that's the answer here. Now, what happens in the situation for subspaces? So let's take K, a subspace of Qn with dimension of K is K. And we want the same thing, the number of L subspaces of Fqn such that dimension of L intersect K, J equals, well, the formula will be somewhat similar. You will have, you pick the J intersection from K, and then you what's the remaining number of ways to pick the rest? Well, there is a Q that comes into play, and you get Q times K minus J to the power K minus J, L minus J, and here you have N minus K, choose L minus J. So I'll leave it to you to think about this exercise.